Let's return to the idea of the electric field of a point charge. And let's put that point charge at the origin for right now. And so if you recall, the electric field of a single point charge is just 1 over 4 pi epsilon naught, q over r squared, where r is the distance between the charge and the point that you're interested in the electric field at, and then r hat. And we can, in fact, imagine this being in spherical coordinates now, because the electric field will always point radially away from the charge, and so that's in the radial direction in spherical coordinates. Now, the interesting thing, it turns out, is that this electric field for a point charge is a very special vector. It's special because, well, it's, at least for a static electric field, it turns out that the curl of this electric field is 0, which means that all of the components of the electric field are not really independent of each other. In particular, the derivative of the x component with respect to y happens to be equal to the derivative of the y component with respect to x, and so on for the other directions as well. So the different directions of the electric field are all actually related to each other, and so they're not completely independent of each other. Well, it turns out that this is connected to another surprising fact about the electric field, which is that you can write the electric field as the negative gradient of some scalar field. And we call that scalar field the electric potential. Now, we've heard about the electric potential before in other contexts in physics, and here we're just going to be generalizing this to the more general vector calculus perspective, where we're thinking about it as a vector in 3 dimensions and using the full language of things like partial derivatives and gradients. Okay, so what's the electric potential for a point charge? So the electric potential for a point charge looks very similar to the electric field for a point charge, in that it's 1 over 4 pi epsilon naught q over r. Now there's some important differences here compared to the electric field for a point charge. In particular, there's no 1 over r squared, that's a q over r. But even more importantly, there's no r hat. There's no direction for this. It's a scalar field. It has no direction, so there's no unit vectors that show up in the electric potential at all. And that makes things a lot nicer. We only have to worry about a function, one single function, rather than a vector. So how do we know that this is the electric potential for a point charge? Well, it's because here I just guessed it, but let's just check it by taking the gradient of this electric potential and show that we get the electric field for a point charge. So if we take the gradient for a point charge in spherical coordinates, well, in spherical coordinates, when we take a gradient, we have to be a little bit more careful about taking a gradient. So we look this up, and so it turns out we have to think carefully about the r, the theta, and the phi directions in spherical coordinates. But we really don't need the theta and the phi directions, even though they look kind of complicated, because it turns out, since the electric potential for a point charge does not depend on the angles, theta or phi, then these partial derivatives are just going to be 0 here. And we only have the partial derivative with respect to r in our gradient. And that's going to point in the r hat direction, so we can see where that r hat direction is going to come for the electric field already. Let's insert our result for our guess of the electric potential for a point charge. The 1 over 4 pi epsilon naught and q are constants, so we just pull that out of the derivative. And so we have a derivative with respect to r of 1 over r, and then all of this is times r hat. And that derivative gives us minus 1 over r squared. So putting all this together, I can find the electric field for a point charge, which is minus the gradient of the electric potential for a point charge, is just 1 over 4 pi epsilon naught q over r squared r hat. So it worked. It gave me the electric field for a point charge, as I expected. Again, that was because we cooked it up to make that way, but you can see how this calculation would go through in finding the electric field once we have the electric potential. This was the simplified case if the electric charge was at the origin, but if the charge is not at the origin, then we need to be a little bit more careful about how we use our variables and how we write down the electric potential. So what does the electric potential look like in this case? Well, as with the electric field, we need to define some vectors. So I'm going to define a vector r and a vector r prime. The vector r points to the point P I'm interested in the electric potential at. And the vector r prime points to my charge. And then the vector curly r points between them from the charge to the point. And in that case, then the electric potential of the point charge, not located at the origin, is 1 over 4 pi epsilon naught q over curly r, where curly r here is just the magnitude of the distance between the charge and the point. Notice again that there's no curly r hat here. We don't have to worry about any unit vectors. We don't have to construct the unit vector curly r hat. All we need is the magnitude. That's it. So you don't even really need to know what the vector is, as long as you know what the magnitude is. Then you can write down the electric potential. So it's a lot easier because of that. If we have a lot of different charges, well, then we look at the ith charge and we do the same thing. For the ith charge, we find the curly r vector between the ith charge and the point P, and then we just add up the electric potentials for each of the point charges. So this is a sum over all the I charges. And this is similar to how we would have done it for an electric field of a point charge. We would have just added up the electric fields. Here we're just adding up electric potentials, and the advantage again is we don't have to worry about direction. For a continuous charge distribution, well, a continuous charge distribution is just a continuum limit of many charges. And so we imagine cutting up the continuous charge distribution into little pieces dq, and then we construct little vectors r and r prime for that little bit of charge dq, and then a curly r for that little bit of charge dq. And the electric potential is then the integral of dq over curly r with the 1 over 4 pi epsilon naught out front. Again, this looks very similar to the expression we would have had for an electric field of a continuous charge distribution, but again, without any vectors.